Hi there, welcome back to the formulaic approach. In this video, let us talk about vectors and scalars. So the goal of this video is that every student that is watching this video as much as possible should be able to, at any level, be able to understand the concept of vectors and scalars from beginning to the end. I mean, at least most of all that you need to know about vectors and scalars. So I'm going to, for that reason, take it from the scratch and build it up and make sure that you see it to the end in order to be able to understand all that I am saying. So if you are also already doing complex stuffs with vectors and scalars, such as dot product and cross product, and it's not even making sense to you, don't worry, this is the video for you. You are going to understand the concept of dot product and cross product, how it was invented, I'm going to build it up all to that, the IJK, vector notation, and all of those things. So by the grace of God, that is what we're going to be doing in this video. So do well to watch it from beginning to the end. And of course, if you think you already know it, you can skip to that point in the video. I mean, know the beginning, so you can skip to that point in the video where we'll discuss that. Now, let us, by the grace of God, or God helping us, start now. So we have vectors. Now, what is a vector? A vector or vectors are quantities that have both magnitude. They have both magnitude and direction. They have both magnitude and direction. Now, what about scalars? Scalars, on the other hand, are quantities. Scalars are quantity that have magnitude only, but no direction. Now, this definition may not make sense to you, okay? So let me make it make sense to you. Now, we have two quantities that I'm going to first use to explain, and those are the quantities of distance and displacement. So the way we arrange it is such that, the way we describe it is such that distance is a scalar quantity, while displacement is a vector quantity. Now, what does this mean? That means that distance has only magnitude and displacement has both magnitude and direction. All right, so what does magnitude even mean? Magnitude means size, okay? Magnitude means size. So for example, if I say I am 6 feet tall, it means that 6 is the number that represents my height in feet. Is that clear? So that is the size. That's size, quantity, the number. Okay, that's magnitude, the number, the value that represents it. So that is magnitude. Now, how does distance and displacement explain vector and scalar? Now look at this particle, for example. This particle moving from a point A along this path to point B. Now let's bring it here. Let me bring it somewhere here. To a point B, for example. Now, if you look at this body moved like this from point A. Moved from point A along this path like this, and made its way to point B. If you are asked to calculate the distance of body A, now all you need to do is take this entire length throughout, calculate this length, okay, by differentiating, by taking small units of the distance dr, and adding, summing it all up. I'm integrating the dr, to get the entire length. Why are you integrating? Because it is curved, okay? So I'm just saying, take the entire distance, the length throughout to get to this point. That is the distance covered by this body. But if you are told to find the displacement of the body, the displacement of the body is different. The displacement of this body is actually the shortest distance from the starting point to the stopping point. This is the shortest distance from the starting point to the stopping point. So it is irrelevant whether he has moved here and here and here and here and here and here and here before getting here. The displacement of this body is the length of this straight line joining the starting to the finishing point. Does that make sense now? That straight line joining this place to this place, that the length and in what direction is displacement. So what we'll say is we're going to draw a Cartesian plane here, or our coordinates, our cardinal points, so that this becomes this is north, this is east, this is west. So this direction will be north, will be south, sorry, this is west, will be southeast. This direction of what? Southeast. So, and in this length is going to be from here to here. So whether it has moved in this curved path does not matter in displacement. It only matters in what? Distance. Do you understand now? So that's the difference between distance and displacement. Let me give you another example since I drew cardinal points just now. Look at, what if this body, a man, for example, move along this path like this. So this man now is moving. Okay? So moves from a point A, begins at a point A and moves to position B. So this man moved from position A to position B, 5 kilometers, moved 5 kilometers to position B. Then changed his course. So he moved due east, position 5 kilometers due east to position B, moved, let's say 3 kilometers now. 3 kilometers due south to position C. Let's put C here. To position C. And now moved, let's say he now moved 5 kilometers away again in this direction to position, what direction is this? West to position D. Now, the question now says you calculate the distance moved by the body. If you are asked to calculate the distance moved by this man, his distance is going to be the sum of all the distances, sum of the length of the entire journey. So what's the sum of the length of the entire journey? That's going to be 5 kilometers plus the next journey, 3 kilometers, plus the final journey, which is another 5 kilometers. And by the time you add that up, 10, 3, that's 13 kilometers, 13 kilometers in distance covered by the body. But what about the displacement of the body? What will be the displacement of the body? Now the displacement, like I told you, is the shortest distance away from the starting point, right? And in direction also. If you look at this position D is just below position A, exactly below position A. So, and if you look at it, it forms a rectangle in this case. So since it forms a rectangle, this place is going to be equal to this place. So he has only traveled 3 kilometers due south of position A. The displacement of this body is just what? 3 kilometers, not 13. Is that okay? So you see that the distance, the magnitude of displacement is different from the magnitude of distance here, right? Because in distance, we are looking at the entire length of the journey. But in this case, we are looking at just the position, okay? Now, look at here. What if I said this body now moved to a position E, traveling 2 kilometers, for example. So I now say, what's the distance away from it? What's the displacement of this body? The distance has changed first because it's now at position E here. So we have to add that 2 kilometers here. So if we add 2 kilometers here, it means this body has covered 15 kilometers in total. But in displacement, he has only covered from here to here. If from here to here, we'll just trace it here. From here to here is 3 kilometers. And from here to here is 2 kilometers. Then here to here will be 1 kilometer. So his displacement has changed to what? 1 kilometers. Still due what? South. Do you understand now? Now, what if the body did not move to did not get to position B. Let's say D. Let's say it stopped at position C. Let's say this body stopped at position C. I'm trying to explain vector and scalar for you, okay? Now, what will be the displacement of the body? First, if the body stopped at position C, let's say it stopped here at position C. Did not move, okay? Now, what will be the distance of the moved by the body? The distance moved by the body in this case is going to be 5 plus 3, that is 8 kilometers. But if you are to calculate the displacement, you will follow the same principle like I said, the shortest distance from the starting point. So this is the starting point, this is the finishing point. So you draw a long line that joins the starting point with the finishing point, and then you calculate at as right angles. So the displacement here is going to be the length of this place, which is going to be hypotenuse, right? So that becomes x squared, which is equal to 5 squared plus 3 squared. So x will become the square root of 25 plus 9. That's going to be 34. The square root of 34 kilometers. And this will be the displacement. That will give you approximately 5 point something. Say 5.8 or so. So do you notice something? Do you notice that this guy, this value is also less, it's still less than the distance traveled. This displacement is the shortest distance away from the starting point. Is that clear? All right. So you can see now, so you have to also put the direction here. So 5.8 kilometers due where here. This direction is what? Southeast. Okay, like I used before. Southeast. Do you understand now? So that is, so you will now notice that displacement tells you both magnitude and direction, while distance tells you only direction, only magnitude. Now, another one we use to explain is velocity and speed. Now, you are going to understand, you just stick with me. Now, what is velocity? Velocity is, they pretty much tell us how fast a body is going, right, with time. How fast the body is going. Okay, so if they tell us the same thing, how are they different then? We tell you that velocity is a vector, I will tell you that speed is a scalar. V for V, S for S, right? Yeah. Alright. So now what is why is velocity what is the difference between velocity and speed? Now I usually give this analogy. If so for example, if someone cooks, if someone says I ate rice, or I ate, yes, let's say you come to me and say, what did you eat? Say, I ate rice. If the person tells you I ate rice, the next question you should ask should not be, was the rice cooked? Does that make sense? If you ask that if you ask if the rice was cooked, then you are wrong, because the person could not have eaten an uncooked rice. So by telling you there that I ate rice, then it means that cooking is implied. That is, everybody knows it must be cooked. So the reason why you see them use this velocity and speed in your textbooks is because when velocity is being used, there is reference to direction there. That is, the direction is known by the speaker, by the person who is saying that statement. Does that make sense? But speed does not give reference to direction. Just like when I say I ate rice, you definitely know that it was cooked. Okay? But if I said I ate rice and you say what type of rice, so that makes sense, because that one does not tell us rice can be of different types, right? You can eat different types of rice. So that is why that is what speed is. You know, there's no reference to a particular direction. Okay? But with velocity, there's reference to direction that is known by the person that is speaking. Is that clear? So that is the difference between speed and velocity in terms of explaining vectors and scalars. Speed has reference to direction, has no reference to direction, while velocity has reference to direction. Now let's talk about the examples of vectors and scalars. So I'm going to take it quickly. I'll be a little faster now. Now, what are the examples of scalars and vectors? Now, I usually use a mnemonic. Okay, so I change the mnemonic pattern, but let's just see which one will work this time. MFM, VER, WAP, T, M, D. If I remember more, I'm going to give you. So this is my vector mnemonic. Now, what is M? M is not mass. M is momentum. I like to write this first. MFM, VWAP, TMD. MFM, no mountain of fire, okay? Now F, force, okay? The other M, moment. And this V, velocity, like we rightly said, not volume, okay? See, this is the reason why I'm giving you this mnemonic. Once you know all these ones I'm telling you, know it offhand. No matter, most of the college exams are going to have right that we ask which of these is vector, which of these is scalar. All of these are the ones that will come out in your vectors. Any other one that is different is most likely going to be a scalar. Not always so, but it's most likely going to be a scalar. E is electric field intensity, electric field strength, or electric field intensity. They mean the same thing. Is that okay? And I have a video on that already. W stands for weight, not work done. Not work done. Weight, not work done. Then A stands for acceleration. And okay, anyway. Then P stands for not pressure. P is not pressure. P will stand for position. T will stand for thrust or tension in string. Thrust is a force in fluid and tension is the force on ropes. So you can see it's force. There are still forces. Weight, force. Thrust is still force. Drag, do you understand, is also force. So if this way is drag, okay, this is not even drag, this is displacement. So drag is also a force. Is that clear? Then this one is displacement, not distance. Like I said, distance is scalar. What does this M stand for? Magnetic field strength. Now listen to me, or magnetic field intensity, or magnetic vector. Now look at this now. You see, all of these are your scalars, are your vectors, are your vectors. Now every other one that comes, pressure, area, length, work done, power, pressure, which one again? Impulse, electric field flux, magnetic flux, all those guys like that, they are going to be what? Scalars. All those guys, mass, they are going to be what? Scalars, etc. But these ones here are the vectors that you mostly need. Most of the vectors that you need. MFM, VWAP, TMD. Once you remember this and you know what they stand for, the rest are most likely going to be scalars. Most of the time. All right. Now, let's talk about the types of vectors. Okay, now we have two ways we classify vectors. Okay, the first classification is based on their nature. Okay, then the third classification is based on like their function, more like their function. Okay, so based on their nature, we classify vectors as free vectors, then the line located vector, line location vector or line located. Is that okay? Then we also have the point located. Now, what's a free vector? Now, free vectors have both magnitude and direction. All these vectors have both magnitude and direction. But free vectors, the difference between what makes free vectors different is that they do not point to a particular. They do not have. Let me explain now. Let me use displacement, for example, is a free vector. Why? Because if I say 5 kilometers due south in this place, if I go to another location, I can take 5 kilometers due south, and it will not be this place again. Does that make sense? So it's a free vector. It can change from place to place. Is that clear? The line located or line location vector or line located vector is one that exists on a straight line. Is that okay? So, for example, force is a line located vector. If a force is acting on something now, we use lines to represent the direction of the vector. Do you understand? So that's a line located vector. Then a point located vector is a vector that acts at a particular point. So maybe a steepy point on a graph or on a shape. Do you understand? So those are that's a point located vector and this is a line located vector. And point located vectors are specific for a location. Point located vectors are specific for a location. All right, now let's talk about the other types of vector. Now this one is based on function and their appearance, their the way they interact. Okay. Now we have number one. We have the which one should I start with now? We have like vectors. Let's start with like vectors. I'm going to explain all of this. We have like vectors. We have equal vectors. We have equal vectors. We have collinear vectors. We have coplanar vectors. We have co-initial vectors. Then we have position vectors. Position vector. Then we have unit vector. Then we have which other one? We have position, equal, like, unit, coplanar, collinear, and co-initial. We also have null vectors or null vector. We also have the proper vector. The proper vector. And I think there are about 10. Which other one have we not mentioned? Like vectors, equal vectors, null vector, unit vector, position vector, proper vector, we have coplanar, non-coplanar vectors, which other one? There is one more that I can't remember right now. Okay, so let me charge my other microphone. Okay, so these are the types of vector. By the time I remember this, I'll let you know. Now, what are like vectors? Now, like vectors are vectors that have equal magnitude and direction. Like vectors have what? Equal magnitude and direction. Like vectors, I repeat, have what? Equal, like vectors, equal vectors are the ones that have equal, same magnitude and direction. So for example, if I say vector A, this will represent vector, we're still going to deal with that. If vector A and vector B are equal, then it means they have both magnitude and direction that are equal. They have magnitude and direction that are equal. That is, they have the same size and they are moving in the same direction. Exactly. What that means is this. If I now say you should give me vector A plus vector B, it's the same as 2A or vector 2B. Why? Because, I'm sorry, the magnitude of A plus magnitude of B will give us this. 2 times the magnitude of A or 2 times the magnitude of B. Why? Because vector A is exactly equal to vector B in magnitude and in direction. So those are equal vectors. Now, what are like vectors? Like vectors are vectors that they are equal in magnitude. They have the same direction. Sorry, they have the same direction, but they are not necessarily equal in magnitude. Let me take that again. They have the same direction. So, like vectors have the same direction, but not necessarily equal magnitude. But if they have the same direction and the same magnitude, they are no longer like vectors, they are equal vectors. Is that okay? Same magnitude, same direction. But like vectors means they are going in the same direction. For example, look at vector A. If I use vector A, if I use this arrow to represent vector A, and vector B, I use this arrow to represent vector B. You see that vector A is smaller in size than vector B, but they are going in the same direction, eastward. So they are like vectors, not equal vectors. All right. So what if they have different direction, but the same magnitude? What would they be called? They will be called negative vectors. Exactly. That's what I wanted to remember. They will be called negative vectors. So this time they are equal in magnitude, but they have different direction. They have different direction. So if those vectors, let's say vector A is equal in magnitude to vector B, but is traveling in an opposite direction to vector B, then they are negative vectors. So I've explained this now, explained this three. Now, this is the case with negative vectors. If vector A and vector B are negative vectors, then we can say that vector A is equal to negative of vector B. Do you understand now? So what that means is that if we add vector A and vector B together, we'll get 0. Now, what is a 0 vector? A 0 vector is a null vector. So that's how we call it null vector or 0 vector. A null vector is one whose magnitude, and by the way, magnitude also means modulus. Magnitude or modulus. Magnitude or modulus is 0. So if the modulus of a vector is 0, or the magnitude of a vector is 0, is called a null vector. But if the magnitude of a vector is not 0, then it's a non-zero vector or proper vector. Proper vectors are non-zero vectors. So that's a proper vector. A proper vector is a vector whose magnitude is not 0. So for example, if vector A plus vector B produce a vector C, and the magnitude of vector C is not 0, then vector C is a proper vector. Exactly now. Vector C is a proper vector. All right. So, but my point is, if you add two negative vectors, you produce a null vector. Why? Because they are equal but opposite in direction. But equal vectors, same in direction, same in magnitude. Like vectors, same in magnitude, same in direction, but not necessarily same in magnitude. Like vectors, same in direction, but they may not be same in magnitude. Now, let's go to the next one, which is, let's take collinear vectors now. Now, the word collinear means, co means together, linear means line, right? On the same line. So it means that, so I'm going to explain these three together so you understand them together. Collinear, coplanar, and co-initial. Now look at these vectors here. And look at these vectors here. And look at this vector, this set of vectors here. Okay, this is it. These two. Let's use these two sets to explain. Now let's call this vector A, B, C, D, E. Look at this vector. They originate from the same points. See, they originate from the same points. They are also called concurrent vectors. But because they originate from the same points, why are they called concurrent? Because they're acting at the same time at the same point. But because even if they are not acting at the same point at the same time, in as much as they originate from the same point, we call them co-initial vectors. Co-initial, that is similar origin, similar point, similar starting point. Is that clear? Those are what co-initial vectors. Now, if you look at it well, you see that they are on the plane of my board, right? So think of this board as a flat, very flat, thin paper. So if it's like that, this flat thin paper makes them, and they're acting on that axis, on that plane of the thin paper. This my board is a thin paper now. Since they're acting on that thin plane, then they are coplanar vectors. They are what? Coplanar vectors, but not collinear vectors. Now this is a typical example of coplanar vectors. Look at it. Some are acting downward, some are acting upward, some are acting in this direction, others may be acting in this direction. But in as much as they are acting on the same plane, this is the same plane here now, they are coplanar vectors. They are coplanar vectors. But if I change this plane now to this direction, now these ones are now acting upward and downward, but look at this guy, is no longer acting in the same direction. He's now acting in this direction. If I took my board and flattened it in this horizontal direction, now this is now my plane, my new plane. So they are no longer coplanar in that way. It's only this one that will be acting in that direction now. Do you understand now? So coplanar vectors means they act on the same plane. Now when are they now collinear? Collinear vectors are now, let's say I now join these two vectors together this way. This one that is going down, I bring it here. This one that is going up, I now bring it here from the same point. Notice they are also co-initial, right? But the major point is that since they are acting along the same y-axis, they are collinear. It means they are joined by the same line. They are jointed by the same line, or joined by the same line. So that is what collinear vectors, coplanar on the same plane, collinear on the same line. A vector going like that, another vector is going like this. They are collinear. It means they share the same line. So collinear vectors are usually co-initial. So we have co-initial. Now what are these two vectors? Position vector and unit vectors. Position vectors and unit vectors. Now what is a position vector? The position vector is a vector that tells the position of a vector relative to another vector, of one vector relative to another vector. So for example, if I say I have a position vector AB, now a position vector AB is a vector pointing from position B to position A. Do you understand now? Let me explain this. So you might be confused as to say, why are you not writing it as AB if it's pointing from B to A? Now you see, the one we write first in our position vector is the position of destination, is where we are going to. Is that clear? The destination is where we are going for. So if I say A, position vector AB, it means that you are at B, you are going to A. Does that make sense? So position vector AB is the vector that points from position B to position A. Therefore, position vector BA is the vector that tells you what? The magnitude of the displacement from position A to position B. Is that clear now? To position B. B is our destination, so it's written first. Is that clear? Now, what is a unit vector? A unit vector is the one that has the magnitude of 1 unit. Is that clear? So we are going to be dealing with unit vectors soon. We use IJK to represent them, okay? Now, a unit vector has the formula. We use, if A is a unit vector, we use A hat to represent it, not with arrow now. This is representation for all vectors except unit vector. This one use A hat, and it means The way we find it is by taking the vector A itself divided by the modulus of vector A. Is that clear? We take vector A and divide it by the modulus or the magnitude of vector A. The vector divided by this magnitude tells us the what? The position vector. Is that clear? So those are the types of vectors and their explanation. Now let's go to representation of vector, so that we begin addition, subtraction, and multiplication of vector. And this is where the main deal is. So make sure you stick with me now. You have not been listening so well since. Make sure you are listening very, very, very well now. Make sure you increase your listening coefficient. All right. So we have representation. How do we represent vectors? Representation of vectors. How do we represent vectors? Now, vectors are represented in magnitude and direction, okay? So, but basically, we just use arrows. If I say vector A, this will represent vector A. If I say vector B, this will represent vector B. Is that clear? That's all. But now, how do we now add these vectors, having known how to represent them? So, for example, if I have vector A, usually we use arrows, like I said, right? Given in this arrow like this. And I have vector B, given in an arrow like this. Very small like this. So it means that vector A magnitude is bigger than vector B, right? What if I now have vector C that is going like this in this direction? And I have a vector D going like this in this direction. Now, what will be vector A plus vector B? What will it be? Now, if I say you should add vector A plus vector B for me, see, this is where you add it. Vector A is in this direction, vector B. So we first draw the vector A, okay? The way we draw it is from head of one to the tail of the other. Or your textbook might use nose to tail, is that okay? Because we call this the nose and then we call this the tail. So nose to tail, by nose to tail mechanism, that's how we add the vectors that has the physical representations here, like this. So we have A is these are vector A. To add it to vector B, we'll bring the tail of vector B to the nose of vector A, and it goes like this. You notice the distance is small, right? So that's how we are drawing it. So from here to here is the magnitude of vector A for vector B. Is it clear? From here to here, these are vector B here. Is it clear now? All right. What if I say you should give me vector A or vector B now plus vector C? Now, how do you add it? Where's your vector B? This guy. Just in the direction it's facing. Draw it the way it is in the direction it's facing. Exactly. Then vector C. How is it? Vector C is like this. Notice you must draw from nose to tail. So you cannot come here and draw a vector C is in this. Vector C is in this direction, right? So that's how you will add it. You come and add it in that direction. Now, if you come and put it here, you'll be wrong. Why? Because this will be tail to tail. And you cannot bring it this way because it means you are turning it in the opposite direction. That will be like negative C. Do you understand now? Because if you change the direction, it has become negative C. So this guy here lies like this. This guy lies like this. You are going to come and add it like this. So if I come and bring it here like this becomes vector C. So, but this does not give us a particular the particular answer to vector B plus C. Why? Because they are in different directions. This one gives us a particular answer because they are in the same direction, so we can get the answer directly here. But these guys are in different directions, so to now know the value of B plus C, we have to draw a resultant. The result of this different direction is a resultant drawn from here to this top here. That is going in the direction of one of them. Is that clear? So this will be the resultant of this addition. Is that clear? All right. So that is the addition of vectors. That is addition of vectors. Now, what did I say? You should add vector D, C plus vector D. Vector C plus vector D. Or no, let's add A and D, for example. Vector A and D. Vector A will be like this, the same direction it's facing, and the length, use the length correctly. Then D, how do we add D? If we come and add D here, this tail to tail, that's wrong. If we come and add D here, nose to tail, that makes sense. So it's just this long, for example. Then where will be the resultant? The resultant will be here. Is it clear? So this vector A, this vector D, and this will be vector. These are resultant vector. Is it clear? Now the resultant is the vector sum of the two vectors. The resultant vector is the vector sum of the two vectors. Now how do we now take vector sums? How do we take vector sums? Now this will lead us into first finding magnitude of vectors and then resolving vectors. Okay? Finding magnitude of vectors and resolving vectors. So for example, if I say you should, let's learn how to find the magnitude of vectors. I want to teach us the magnitude first before teaching us major addition and subtraction of vectors, okay? So that you will understand. All right. Now, in case you are also thinking that what if I wanted to do vector A minus vector B? I'm sorry I didn't give that before. In this case, this is the same as vector A plus negative of vector B. So we have to first create the negative of vector B. And what will be the negative vector of vector B? It will have the same magnitude but different direction. So what will happen? If it is facing here, the negative of vector B will face the opposite direction. Will have the same size. Do you understand now? So to add them up, it will be like this and like this. Like this and like this. So this one that is going from here to here is vector B. This one that is going from here to here is vector A. Do you understand now? So what will be your answer? Your answer is going to be this place from here to here. Do you understand now? So that is the magnitude of vector A minus vector B. I hope that is clear. All right. And it is for this one too. It is for the one for, let's say you are said to take vector A plus vector A minus vector C, for example. Now it will be the same as like I interpreted here as A plus negative C vector, right? So what is negative C vector? If positive C vector is going like this, then negative C vector will go in the same direction but in different, go have the same magnitude but in the opposite direction. So this will be negative vector C here. So what you just do is your vector A, then you come and draw. Where will you draw so that it's nose to tail? You can't come and draw here. It will be head to head here. So you come and draw it here at the tail of A. So this will be the resultant of the vector. This will be the resultant. So that is A minus B, A minus C. I hope that is clear. Now let's learn how to find the magnitude of vectors. Now, if I give you a vector like this in physical representation of the vector, now what do I mean by physical representation? You have to understand this physical representation well because that's where the main work is. So now look at this, my markers like this. We use IJK values like our Cartesian coordinates. That's what we use to represent the vectors, okay? So if a vector is traveling in y-axis, so we have the y-axis first. These are our reference points, y-axis, x-axis, and a z-axis. Is that okay? So the way we draw that is something that looks like this. These are y-axis. So there's a vector. Our vectors could be on y-axis. Our vectors, position is also a vector, right? So we could use position x-axis to also show a vector. And we could also use our z-axis. So this is y-axis, x-axis, and the z-plane. Please, you have to follow me in this aspect so that you will understand how we use the IJK vector values to represent them. Now, when a vector is traveling on x-axis, we use the I vector to represent it, I notation. When a vector is traveling in the y-axis, we use the J unit to represent it. All right. I'm sorry, my microphone stopped here. So what I was saying is that there are three planes that we use to represent a vector. Now the third plane you are seeing there is the z-axis, which is going into the board and out of the board. It goes into the board and out of the board. We use I to represent any vector that is moving along the x-axis, J to represent the unit value for a vector traveling in the y-axis, and K for the z-axis. All right, so those are the letters we use in denoting them. And I want you to understand that we use vectors to see in three dimensions. Okay, so vector is employed in seeing in three-dimensional space. So as you can see here, we have three dimensions here. And how do we make those three dimensions out? I'm going to show you here by making three lines. I'm going to make three replicates of each of those lines. So I've replicated the z, the positive z is the outward one, and the negative z is the inward one, the one that goes into the board. So I've replicated the positive y also once. I've replicated it once. I have z, positive z once, positive y once. Now the positive x, we replicate it once, so that's one, which means twice for each of them now. So we are going three dimensions, those are three lines to represent each of the planes. Then we are replicating z the second time, so two replicates of z, the positive z axis, right? That's two times, it's remaining one more. So that's the third time now on that edge there. The third time, we have the z, the third, that's the three dimension for z now. Then the other one now, the y, the positive y, this is the second replicate now. We have, this is the second replicate on that edge there. Then the third replicate here. Okay, that's the third replicate. All right. So now it's remaining the x, the positive x axis now. So we have only one replicate of that. Now we need two more replicates of that. So that will be we have three for the other planes, the x and z, I mean the y and z. So we now make two more for x, one, two. So you can already see that it's seeming as though it were coming out of the board. The box looks like it's coming out of the board. To make it clearer, I'm going to draw another box that is going into the board to make it clearer. So we'll replicate the same way each of those planes three times. So we have replicated the negative z once, the positive y twice, so, and the negative x once, okay, negative x once, we have done negative x once, the negative y once, okay, so then the negative z now three times, so the negative z is complete, negative z is complete. So negative y is now complete. But you know, I drew another one because my calculation was wrong there. I was supposed to use the plane, yes, this second plane, I mean the main plane, the main y plane, okay? The main y plane, but you know, I drew another one. So that's why it's not conforming there. But you can already see that the negative x also has been replicated three times using this main negative x plane. So you can already see that it's looking as though there are two boxes, that one going into the board, then the other one coming out of the board. So that's that's how to see in three dimensions. There is a plane y, x, and z. So this black marker that has faded is the z plane. You can already see that, right? So I'm trying to show us how to employ the vector notation. Now, if you want to look at things in two planes, okay, if you want to use two planes to look at things in this thing, for example, you see that those 2 points that I picked, they will correspond to a particular x value, and that 1 point rather will correspond to a particular x and y value. Okay, so now it has a value on the z plane, Okay, to have a point on the z plane, but because at we are looking in just two dimensions, the z plane is blocked there. Okay, the same way here, I pick a point on that box, for example. Now that point, if we look in two dimensions, there is a second point just under it that has been blocked by our line because it is on the z plane. So that is why two planes are not enough to explain things. That's why we employ vectors. That's why we employ vectors. All right. So now, if I pick a vector, if I have the vector A is going to be represented by my three planes, okay, by values on my three planes. Okay, it's going to have a value on x-axis, on y and z-axis respectively. So it's just like the Cartesian plane. I have a point A represented in magnitude and directions by two coordinate system, but here we use three coordinate system. So, but because they are in units, in different units, we cannot just use 3 minus 1 and 5. We have to put ijk values, which will correspond to different values or different units. Do you understand? The I unit is for x-axis, the j unit is on y-axis, and the k unit is on z-axis. So just according to their values there, I have 3i minus 4j plus 5k. So let me put another vector b represented by 4i plus 3j. Now I want to show you something here. I'm going to use only 3 units here, 3 points here, I mean two coordinates here rather. Two coordinates here. That's 4 comma and minus 3. And a vector c having 2i plus 6j and 2k. Now for that vector b, the k value is 0. Do you understand now? Its value on the z, it means that on the z-axis is at origin. Is at origin. But it has a displacement, for example, if the vector is displacement, it has a displacement of 4 units on on x-axis and minus 3 units on y-axis. So if I have to find the magnitude now, this is how to find magnitude of that vector b. I'm going to use the vector b for an example because it is shown in two planes there. Now if you draw my 3D plane, the k value of that vector b is 0 on z plane because there is no k there, so we assume it is 0 or it is taken as 0. So it means that on z axis our b vector is at origin. Do you understand now? It's at origin, but it has a value in negative y-axis, that's 3 minus 3 and plus 4 in x-axis. So the displacement there will be from 4 to minus 3. So that's the line there. So you can already see a triangle, a right angle triangle given there. So that right angle triangle is going to have a hypotenuse like we normally have and two adjacent sides. So you find it, we use to find the hypotenuse, which is the distance between the point x and y on that the 2 points on x and y axis respectively. We use the Pythagoras theorem. So the same way we're going to use Pythagoras theorem here using 4 squared, taking the square of 4 and the square of minus 3. Do you understand? So that the magnitude of a vector is found using the Pythagoras theorem. Do you understand now? Is found using the Pythagoras theorem. That's why vector addition is different from scalar addition. So this becomes the square root of 16 plus 9 because square of the negative value is positive. So this becomes 25, which is 5 units. Now we use units there because the unit is not specified. If it were displacement, like I said, it would be meters. For SI unit or centimeter, it could be forces, maybe 4 Newton, 5 Newton as the case may be. It's just any vector there. So we put units. Alright, depending on the unit. So what we wanted to get the magnitude of the A vector. We put modulus. Those two lines there represent modulus. This is how we call it magnitude of vector A or modulus of vector A. And it's taken as the square root of the first value squared plus the second value squared, which is negative, plus the third value squared. 3 squared 9, 4 squared 16, 5 squared 25. Keep in mind that if you square a negative value, it will be positive. So square root of all of that, that's square root of 50. Root 50 will be root 25 times 2, that's root 5, that's 5 root 2 rather, 5 root 2 units. Okay, using third. Okay, you break it down to root 25 times root 2. Root 25 is 5, root 2. Then we have 5 root 2 units. So that would be the magnitude of vector A. Now, you can solve vector C by yourself and put the answer in the comment section. Put the answer for the magnitude of vector C in the comment section. Now, what if you are now told to add up vectors? What if you are told to add up vectors? For example, you have vector A plus vector B. Vector A plus vector B. Now, the magnitude of vector A, this is not magnitude yet. You are not adding the magnitudes yet. Add the vectors like that. Add them by just taking those values and adding them up together, okay? Scalarly, add them up scalarly. So you are, you know, you add I to I and J to J. So it becomes 3I plus minus 4J. Let's open the bracket first. Plus 4I minus 3J. Now I intentionally did this so I can see that if it were a negative, it will alter the value of what is in the bracket. So we have 3I, oh yes, plus 4I, so I'm collecting like terms, minus 3J plus 5K. So this becomes 7I minus 7J plus 5K. So that will be vector A plus vector B. Is that clear? This is the physical representation. This is in physical representation. So in physical representation, you add them scalarly. So what we are told to do vector B plus vector A. Now, since you are adding them scalarly, you will get the same answer. You still get 7I minus 7J plus 5K. It's just like saying 3 plus 2. It's the same as 2 plus 3. So that since we are getting the same value, it means that vector A plus vector B is the same as vector B plus vector A. And that principle is known as commutativity. That is, they are commutative under over addition. That is, you can add up two vectors in alternate directions and you get the same value. Over addition, that's commutativity of vectors. Okay? Now, what we are told to do vector A minus vector B, you see now the negative will affect the value, so we have the value in the bracket, the items in the bracket. So we have 3I minus 4J plus 5K minus 4I plus 3J becomes 3I minus 4I, then I put the positive j first, so that's plus 3j minus 4j plus 5k. It becomes minus I, because 3 minus 4 is minus 1, so I have minus 1I, that's minus I, minus j plus 5k. Minus j plus 5k. Notice that the value of k remains the same because it doesn't have a k value. Now, the vector b does not have a k value. Now you also notice that you can rewrite this as minus of I plus j minus 5k. How did I do that? I simply factored out negative so that my vector will begin with positive value. Okay, so if you open the bracket there, you'll get the same answer. Do you understand now? You get the same answer. But now, the operation is not commutative over subtraction, because vector A minus vector B is not the same as vector B minus vector A. So the operation is not commutative over subtraction, but it's commutative over addition. So we call it commutativity principle. Commutativity principle. Now, the next thing we're going to do is Okay, let's add up vector A and vector B. Oh, okay. If you are told to add vector A and vector B, you know you are going to add, like we said before, add nose to tail or head to tail, and the resultant will be that diagonal, okay, that joins the head to their tail of the two vectors. That's the resultant, okay. So the same way here, the magnitude of this one is for magnitude. You notice that the magnitude of the resultant is greater than both vectors, is greater than the magnitude of both of the vectors. Is that clear? So adding those vectors to get the magnitude of the resultant itself, we use two laws. One is the triangle law of vectors, and the other is the parallelogram law of vectors. The first one is the triangle law of vectors, and the second one is the parallelogram law of vectors. Now, what does the triangle law of vector state? The triangle law of vector says that if the two sides of if the two adjacent sides of a triangle are represented in magnitude and direction, the third side, which is the hypotenuse, is the magnitude of the third side is the resultant of the two vectors. Let me state that again. If the two adjacent sides of a triangle are represented in magnitude and direction, the resultant of the two vectors is the third side, is the magnitude of the third side, which is the hypotenuse. The third side of the triangle, which is the hypotenuse. Is that clear? Two adjacent sides represented in magnitude and direction. That is, the first side below there represents A vector, second side represents the one on the y-axis represents B vector. The resultant is the magnitude of the third side. Do you understand? That hypotenuse that joins them. This is triangle of vectors. It works for right angle triangle. So you see that you set up the system such that it's a right angle triangle it forms. But what if it's a case what of a case where it doesn't form a right angle triangle? We are going to see that in parallelogram law of vectors. Now, if you want to get the magnitude of the resultant, you can easily use Pythagoras theorem. That's the hypotenuse square is equal to opposite square plus adjacent square. Our hypotenuse is now the resultant of the two vectors. So the magnitude of the resultant squared is equal to the magnitude of vector A squared plus the magnitude of vector B squared. Is that clear? Now, what about the parallelogram rule of vectors? Now, this one is useful when the two sides you are given, the two vectors do not align appropriately as along the adjacent sides of a right angle triangle. So it says that if the two adjacent sides too of a parallelogram are represented in magnitude and direction, you know that a parallelogram, the two sides are not perpendicular to each other. They are not at perfect 90 degrees to each other. That's what it means. So if it's represented in magnitude and direction, the resultant is the diagonal drawn from the 2 points where they meet. Is that clear? The diagonal drawn from that point is the resultant of the two vectors. I repeat the law that if the two adjacent sides of a parallelogram are represented in magnitude and direction, the resultant is the diagonal drawn from the 2 points where they meet. Is that clear? The diagonal. So that diagonal is the resultant. Now you notice that when I make out a diagonal from this side, from this my parallelogram, the vector B replicates itself on the right side and vector A replicates itself on the upper side there. The angle there, those two angles, theta and theta, they are equal. Is that clear? So the result, so I bring out my my triangle, I'm going to just separate one triangle out of it there. So that triangle there, to get the resultant, I'm going to use cosine rule, which says that the magnitude of resultant is going to be vector A, magnitude of vector A squared plus magnitude of vector B squared minus 2AB, 2 times magnitude of vector A times magnitude of vector B, cosine of the angle between the two sides. Make sure you understand that's just the cosine rule. You should already know cosine rule, okay? um um Cosine rule is just the one that says that if you're looking for example, if I'm looking for a third side of a triangle that is not a right angle triangle, for example, I'm looking for side A, it will be A squared plus it will be equal, A squared will be equal to B squared plus C squared minus 2BC cos theta. Theta will be the angle between side B and C. Is it clear now? So the same way, that side A looks like the resultant between the side B and C that I just used in my example now. Okay? So now the question you are given will determine the method that you will use. Okay, whether it is parallelogram law, the law you use is the parallelogram law or the triangle law of vectors. Now let us go to resolution of vectors, resolving vectors, especially coplanar vectors. We are going to be doing coplanar vectors now. Coplanar vectors. Now the reason why we are doing coplanar vectors is because vector resolution, that's what you see in your exam, WAEC and JAMB, most even in A level, you will not see more than coplanar vectors. So that's why we are using only coplanar vectors for this example. So let's say there is a body. You see that this guy that I drew, this plane that I drew, if there is you see that point, that midpoint there is a body there and there are forces acting on it. F1 is acting at that point, F2 is acting at that same midpoint, middle there, and another force F3, for example, you have F1, F2 and the angles there, okay? You have theta 1, theta 2 and theta 3. And F3, all those three forces, they are acting at that point and they are acting at an angle. Let's have a fourth force called um, F4, okay? Now, if you are given coplanar forces, coplanar vectors like this, I'm using forces because that's the typical question. They use forces for the vectors. You know, forces are, all forces are vectors, right? Okay, so that's why I'm using forces here. Now, how do you find the resultant of all of these forces? Why do we need resultant here? Now, here's the case. Because the angles are not acting at perfect straight lines. They are not acting at one single plane. They are not acting on a single plane. Like for example, they are not acting as not at y-axis alone or x-axis alone. If it is x-axis and y-axis alone, the value of the vectors will just be addition of those two vectors, scalar addition. You get the magnitude, the resultant of the two vectors. They are acting at y-axis to each other only, or x-axis to each other only. For example, look at what I drew here. F1 is acting upward, F2 is acting downward. On that same y-axis, along the same y-axis, you simply take F1 minus F2. Why is it minus? Is because F1 is acting on positive, F2 is acting on negative F. Okay, so if you have something like this, you basically just add them or subtract them as the case may be here. So, but in this case, all my forces are acting, most of the forces are not acting on a single axis. They're acting on at different axes, but they are on one plane. That's my plane of the board there. So they are coplanar forces. Now,
So,
as they are,
what
how
if
do you
we
find the
have to now
resultant?
resolve
You
this
find the
and add up all
resultant
of these
by
vectors?
resolving.
All right.
Reset it and my microphone began to work.
When we
Thank
have
you
to
for
add up
sticking
all
to
of
a
these
good time.
vectors, how
God
do we
bless
do
you.
it?
God bless
Now, we
you.
cannot just, as I said, we cannot just say this F1 plus F2 plus F3 plus F4 plus F5 like that. The reason is because some vectors, some of these forces are not exactly on X component or on Y component, and they are not exactly on X component. They are lying in between. And if they lie in between, it means they have both components. It means they have both X, both Y, and X components. That's the meaning. Alright, so what we have to do is we have to resolve them to all of their components. So for example, we have both components, Y components, the people that the forces on Y component or vectors on Y component, and the vectors on X component. So by separating them this way, we can now take the resultant, okay? So that we know the forces that are exactly on Y component, we call them Fy, and the forces on X component, we call them Fx, so that this will now be the resultant. Do you understand? Good. And to find the resultant that way, you know the formula will now become what? The square root of the summation of all the forces on Y component and the summation of all the x's, all the forces on X component. And then we'll have our answer for the resultant.
So if we want to resolve these forces, we want to add up all of these forces, we cannot just say this plus this plus this plus this plus this, because they are not perfectly on x-axis or perfectly on x-axis or perfectly on y-axis. So what do? We have to sum up all the forces in a way that is vectorial. So how do we do that? We have to first bring the forces that are in the same these forces are acting at angles, right? So we have to resolve them to our reference positions with our x and y axis. So how do we resolve that? How do we do that? Let's take some forces that are on y component and the ones that are on x component. So how do we do that? Which forces are on x component? Now I've written this because I've proven this before, okay? My microphone stopped just now, so I needed to come back and check. So to open an angle, you use sine. To close an angle, cos. C-O-S, cos. Open, N. I don't know, just remember. When you open an angle, you use sine. When you close an angle, you use cosine. So to resolve, you have to resolve all these forces on x and y components. Starting with F1. To resolve F on x and y components, we want to start with this y component of forces. This one that is lying at an angle here, it means it has both x and y component. At an angle, x, y and x component. At an angle, y and x component. So how do you resolve F1, for example, on y component? You bring it here, right? You bring it here. So if this is our y component as this, then this is F1. How do you resolve it to y component? By bringing it like this. Does that make sense? You know this is your angle here. This is your angle here. This is another way to prove it. This is our x component here. You want to bring it to this component. So what are you doing? You are opening up this angle. You are opening. So that will be sine. So it will be F1. But it is negative while you are going. So it will be minus F1 sine theta 1. Alright, for F2, we are going, just rewind if you don't understand what I just did. Just rewind. Now, for F2, we are going to y component. So if this is our F2, we close this theta 2 and it's negative 2. So it will be minus F2 cos now theta 2. Is that clear? So let's say this angle was 40 degrees and this is 3 Newton, for example. This will be minus 3 cos 40. Is that clear? Cos, because we are closing this angle. Can't be 40, it should be around 30. Alright. So for F3 in this case, you see I first drew my reference point. We are going Y. So to go Y with F3, how do we go? We close theta 3. Well, it's positive, so it becomes F3 cos theta 3. For F4, F4 is perfectly on y-axis, so we'll just write F4, no sine or cos anything. Or if you think of it as this way, as you bringing it all the way from x-axis, you are opening up 90 degrees. To open up 90 degrees is that's sine 90, that will be 1. And if sine 90 is 1, then F4 is going to be maximum. F4 is going to be F4. That is F4 sine 90. That is still F4 because sine 90 is 1. Alright. For F5, which is the last force there, it is on x-axis. It is not on y-axis at all. So, but if you try to do it, you do it like this. Bring it all the way from x-axis to y-axis. You close 90 degrees. By closing 90 degrees, that's cos 90. and that's what? 0. So 0 because, especially because this guy is not on y-axis at all. Then for the x component of our forces, we have F1. What we'll do to take it to x component is to close, look at it now, we'll close theta 1, right, by bringing it here. So by closing theta 1, it's still negative, so F1 cos theta 1. Is that clear now? Because it's still negative side of x, negative side of x. Therefore F2 is here, it's going to come here by opening, see, it's going to come here, here's F2, to open up this angle, right? And it is coming to positive axis, so it will be F sine theta 2. Do you understand now? Then for F3, it will be, to come to x axis, it will be opening up theta 3. So that will be F3 sine, open, sine theta 3. Then F4 is not an x component at all, so it will be 0. Because if you try to bring it, force it to any of the x component, that's closing 90, that's cos 0, that's 0. Then for F5, it's perfectly on y-x axis, but it's negative, so that will be negative F5. So by the time you do that, you'll be able to take the summation of all the forces on y component and the summation of all the forces on x component. Then the resultant will now be like this. See, you have been able to take all the forces, put it on x component, y component. These ones are now perfectly on y component. These ones are now the ones perfectly on x component. So by the time you want to take the resultant will be this. Does that make sense now? So we now have f sub y and f sub x. These are all the ones on x and y components respectively. So by the time you want to take the resultant will be hypotenuse square, right? Equal to opposite square, anyone could be opposite, summation of fy plus adjacent squared, summation of fx component squared. So by the time you want to do this, you take square root of both sides, square will cancel square root, and then you have square root of this. So our answer is resultant force, magnitude of resultant is equal to the square root of summation of forces on y component squared plus the summation of forces on x component squared. And that becomes the value of your magnitude. Then what if we are told to find the angle between them? Now, if you are told to find the angle between them, whether it's this angle or this angle, if it's this angle, theta, for example, this will be your opposite, this will be adjacent. If it's this angle, this will be your opposite, this will be adjacent. Either ways, you come up with opposite and adjacent. And which function, which trig function compares opposite and adjacent? That's tan. So we have tan of theta to be equal to opposite, which is fy in this case. We are using this opposite, which is summation f sub y over summation f sub x, and that becomes our tan theta. So that theta will be equal to the tan inverse of the summation fy over summation fx, and that becomes our angle, the direction. Is that okay? This is how to find direction of the forces. All right. So that is that for resolution of forces. Now, how do we now excuse me. So that's how you resolve vectors. Now let's now go to vector multiplication. Now there are two ways by which we multiply vectors. There are two ways, and I want you to stick with me here. So this is where we are talking about the dot product or scalar product and cross product. We have dealt with resolution, we have dealt with addition, yes. The resolution is part of the addition and subtraction, okay? So let's now go to the what's that now? The multiplication of vectors. Now there are two ways by which you multiply vectors, and they are the dot product or scalar product and cross product. So we are going to begin with the dot product. So now I'm going to explain to you how scientists came about what is called dot product. Okay, how they came about what's called dot product. So now dot product, first know that dot product is the sort of multiplication that gives rise to another scalar. Is that okay? When you dot product gives rise to another scalar quantity. Dot product gives rise to another scalar quantity. Dot product, I said, gives rise to another scalar quantity. So now, let me first show you the formula. Then I'll show you how this formula was derived. If I say vector A dot vector B, the formula is vector A, the magnitude of vector A, times the magnitude of vector B, cos theta. Now, how was this formula gotten? You see, there are two phenomena that we use to explain. You see, we have work done. The formula for work done is force times distance, right? I'm using R for distance. Torque also is force times distance, but in this case, they produce different things, different results. So mathematically they are the same, but the result is actually different. This one produces linear motion, this one produces rotation. So let's show you how so this one is for dot product, this is for cross product. Now let me show you how. Now if I have a body, a mass on this ground, a body of mass M on this horizontal floor like this. Now, and I said a force is applied in this direction. Watch. I apply a force in this direction to pull it in this direction. So a pull is applied on this body. And the body eventually moves from here. The body moves to this point here. The body moves to this point here. So it means the body has moved from this position to this position, or from this position to this position. So the body has moved from here to this place. So this is the displacement of the body. This is what? The displacement. Force times displacement, or distance if you care. So as we are looking at it here, this body has moved this distance R here. Okay? If I say calculate for me the work done, you simply multiply the force times the displacement. Is that clear? But this is only easy, this is only possible because this force is in this direction. You do it directly like that. What if this force were not acting in this direction? What if I give you a second scenario where the force is now pulling in this direction? What? A force acting in this direction now, and it produces motion still in this direction because it is pulling to come in this direction, isn't it? This force is now acting at an angle to the horizontal. So what we have to do is we cannot just say force times distance here. We have to resolve it to this horizontal. Then you now ask me, but master, there is also vertical component here. Why can't we resolve it to the vertical component and take the resultant? Now listen, this is where the dot product now comes in. Why are we not resolving this to the f sub y component? So we have f sub y component and f sub x component, right? There are two components of these forces. Why can we not resolve to the y component and the x component the same way? The reason is this. This Fi component, let's analyze it. Where does this body move? This body moves in this direction, cover the distance r, for example, displacement r, for example. So if this body moves from here to here, then what is the contribution of the f sub y component? 0. Because f sub y component is going to be acting downward, pushing it down, or acting upward. And is this body coming up? This body is not coming up. This body is not moving up. This body is going in this direction. So for a force acting at an angle, is only the f sub x component that is effective, that is causing motion. So this f sub y component is not contributing to the motion of the body. the F sub x component is the one contributing to the motion of the body. So how do you get up? So we'll say that work done in this case therefore becomes what? The force, which of the forces? The F sub x times R. You remember, so you know that it's not F sub y, right? Because F sub y is not causing motion. F sub y is balanced by the weight of the body. F sub y is going to be the weight of the body and is balanced by normal reaction. Is that clear? So that's 0. So F sub y is not causing motion at all. But F sub x is the one causing motion. Is that clear? So just stick with me. I'm going to show you the physical representation of this. Now, F sub x is the one causing motion. So we are going to resolve this guy to the x component. Now, how do you resolve it? It becomes, to get F sub x will now be equal to what? F, our normal force, our actual force, close this angle, because by resolving it to this component, what are we doing? Look at it. By resolving to this component, we are closing this angle, right? So it will be F cos displacement. So these are two vectors here. So this is F sub x times displacement. So you can see that the work done is equal to what? F dot R cos theta. So how do we now define scalar product? Then we say that scalar product is the product of the first vector. Product of the first vector and the components of the second vector that is in direction of the first. Let me explain that. See, you notice that Fx is in direction of R, right? Where is displacement? Displacement is in this direction. This body is moving in this direction. So its displacement is in this direction. So you see that it is Fx that is also in this direction, right? So the dot product is defined as the product of the first vector and the component, the product of this first vector and the component of this second vector that is in the direction of the first vector. But I arrange it the other way around here, right? So that will be W equals R magnitude, the component of this first vector, times the component of this second vector that is in the direction of the first vector. Is that clear? So that is what we call dot product. Now, in physical representation, what do we mean? What will this be in physical representation? So now listen, in physical representation, that is in 3D perspective. Now what we see in 3D. Now, you see, now stick with me. If I use my vector A, for example, to have AX in x-axis, so AXI plus AYJ plus, I hope you understand what I'm doing, AYK, that is my A on x-axis with I unit plus A on y-axis with J unit and A on z-axis, z-axis. These are my unit vectors, right? Now, and I say vector B, my second vector, is BXI, yes sir. Shall I repair one? Yes. It's locked, sir. Yes sir. So BXI plus BYJ plus BZK. So this is going to be, okay. So this is going to be our physical representation of the two vectors A and vector B. Now if I say take the dot product of this vector for me. Now, remember that I said it is the component of the first vector times the component of the second vector that is in direction of the first vector. There will be two components of the second vector. So it is the component of those two components, it is the component that is in direction of the first vector that will multiply together. That is dot product. So if I say take dot product of this form, A dot B, how do we do this? Now, Let me put them in bracket together. I want you to understand this explicitly. That's why I want to elaborate it this way. AXI plus AYJ plus AZK multiplied by BXI plus BYJ plus BZK. Now it becomes this times this is going to give you what? AXBX I dot I. Make sense? Plus now. You remember that we said it has to be cos theta, right? Okay, so I dot I cos theta. Is that clear? Everything here is multiplying each other. I'm just putting this in bracket because they look alike and I want you to see something. Cos theta. Now plus this will multiply the second one. That will be AXBY I dot J. I hope you're understanding. I dot I cos theta. Cos theta is from the formula we obtained here, right? Before we talk about the angle, I'll tell you what the angle is. Just calm down. AXI times BYJ will give us AXBY, then in bracket I dot J cos theta as well, plus this guy times the third guy. That becomes AXBZ I dot K cos theta plus, now this guy has multiplied everybody here. This guy now multiply everybody here. This times this times this times this. That will give us AYBX J dot I cos theta plus AYBY J dot J cos theta, then plus AYBZ J dot K cos theta plus, now this last one, now multiply everybody again. AZBX K dot I cos theta. I hope you're understanding me. Plus AZBY K dot J cos theta. Just know that it's cos theta that is there. Then plus AZ, we are on AZ BZ K dot K cos theta. Now, let's now write the final answer. What will now be the final answer in physical representation? We have A dot B will now be equal to this. Remember, what is the angle? What will be the angle between I and I? Where is I axis? X axis, right? Another I will be on the X axis, right? What will be the angle between them? 0 or 180 degrees, right? So, but it's actually 0 we use because we are thinking of them as being parallel to each other now. So that's 0 degrees. So if it's 0 degrees that is between them, cosine of 0 is what? 0. So if cosine of 0 is 0, then cosine of 0, that's 1. Cosine of 90 is 0. Please check on your calculator. Cos 90 is 0. Cos 0 is 1 because sine 90 is 1. We did it here. Sine 90 is 1. So sine 0 is 1 that gives 0. Is that clear now? Alright, so remember this. Just use your calculator, you're going to get that. Now, so what's the angle between I and I? They are in the same direction, so the angle is 0. So cosine of 0 is what? 1. Cosine of 0 is 1. So what does that mean? This place will give us AXBX times 1. That is AXBX. Plus, here, AXBY. I dot J. J is y-axis. J is y-axis. Look at it. J is y-axis. Sorry, let's start with I. I is x-axis. J is y-axis. So I dot J is what? It's going to give you, this is 90 degrees, right? So cosine of 90, because it's 90 degrees that we have between them, right? Cosine of 90 is 0. So everything in here will give us what? 0, because this times 0 is what? 0. Does that make sense? Good. For the next guy, AX busy, I dot K. K is on this axis, that is outside the board. Look at it. K is outside the board, coming out of the board, and I is on this axis. What's the angle between them? Also 90 degrees. They are perpendicular to each other. So 90 cos 90 again, 0. So everybody here, 0. So let's now do this. So it means that this one, Ji will also be 0. Why? Because it's 90 degrees between them. So cos 0 is 0. This guy now, J dot J, the same angle, they are going in the same direction. So since they are going in the same direction, angle between them 0, cos 0, 1. So this becomes plus AY BY. Then plus, for this guy, AY BZ JK 0, because 90 is between J and K again. KI 0 again, because 90 is between K and I. Plus KJ 0 again, because 90 is between J, K and J. Then K and K 0 degrees, cos 0, 1. So we have plus AZBZ. So it means that our final answer, A dot vector B, will become AX BX plus AY BY plus AZ BZ. And this is how we find our dot product. So when you see that, when you are told to just multiply this and this and this and this and this and this, it's correct, because if you multiply this with any other component for dot product, you will get 0. Is it clear now? So, and that proves the assumption here that to get a value in dot product, it is when you multiply the component of the first vector and the component of the second vector that is in direction of the first vector. The first vector is in direction I. So it is when you multiply it with someone in direction I that you get a value. If the first vector is in direction J, it's when you multiply with the guy in direction J that you get a value. If the vector in direction K, it is when you multiply with the vector in direction J, direction JK rather, that you get a value. If you multiply with any other one in another direction, you get 0. Is it clear? God bless you for getting it. All right. So now, this is our formula. This is the physical representation of what? Cross dot product. Now let me do physical representation of cross product, so you will understand. Or let me just quickly give you an example. So look at this example now. So what if I now said, just so that you will know, so master this please. So sometimes you as if it's confusing me. It's not confusing, no? Cos 90 we said is 1. No, cos 90 is 0 now. Cos 90 is 0, yes. See, I normally forget 2. Then cos 0 is now 1. Makes sense? Then sine 90 is 1. And sine 0 is now 0. Okay, that was what we said, right? Yes. Yes. Because cos 0 here gave us 1. Good. All right, let's go now. So now look at an example here. Vector A is what? Let's say 3i plus 2j minus 4k. And vector B is I minus 2j plus 3k. And I say find the physical representation of this vector. What will be the physical representation of A dot B, the dot product? If you are not given the angle, just take the physical representation. That becomes this times this. 3 times 1i plus, because in this case we had dot I, makes sense? So plus 2 times minus 2 j dot j plus minus 4 times plus 3. Minus 4 times 3. K dot K. So by the time you do this, this will give you 1 because cos of 0 is 1. So our answer will be 3 plus Okay, in units, actually, you'll be given an angle. You'll be given an angle. But the point is that by the time you multiply them together, you're going to get your answer exactly. So it will be 3, the guy on x-axis. So let's put it as 3, let's just say, no, let me prove something to you first. If we do this, let's take the magnitude. If you take the magnitude, A dot J in physical representation will become 3 times 1, like I said. Oh, I'm not supposed to clean that. Just do 3 times 1, that will be 3i. Now listen, I is unit vector. The magnitude of unit vector we said is 1, right? So it will be 3i minus 4j minus 12k. So it's the same as what I wrote. So by the time you take the magnitude of this thing, it will be the same as taking the magnitude of this times the magnitude of this. How about test that? What's the magnitude of A? The magnitude of A will be square of this. The square root of this 9 plus, I've told you how to find magnitude, right? Square of this 4, square of this 16. This gives us 29. Square root of 29. Okay? Then the magnitude of B is going to be the square root of 1 plus 4 plus 9. That becomes 514, square root of 14. So if we multiply this together, root 29 times root 14, that will give us root 29 times 14. That's going to give us 4 and this 36, 7. So we have 290 plus 76. So that gives us 6. 366. So square root of 366. Square root of 366. You can break this down further, of course, you can. Right? But let's leave it this way. Now let's check on this guy. Let's check on what I gave you here as the answer. Square this guy gives us 9 plus square this guy 16 plus square this guy gives you 144. Okay. This gives us, supposed to give us relatively the same value. This plus this, that's oh, okay, yeah. This by the time you take it doesn't give us a square root of 360. What mistake did I make? I'm coming to this. You know that. Okay. You are weren't giving an angle here. Let's say you were giving an angle here. Angle, let's say theta was 30 degrees. Sorry, I'm stressed already. I've been shooting for 2 hours. So you take the magnitude of this by doing that thing we did, and the magnitude of this times cos 30. So like we did there, we got root 29 for this one and root 14 for this one, then times cosine of 30. So that will be root 3 over 2 times root 14 times root 29. By the time you do this, you will get the answer of 4, A dot B. Sorry for the mistake, please. Let's go to cross product, please. I promise you understand how the formula of cross product too. I know that's when I usually confuse students the most. So, physical representation now for cross product. I'm going to teach you with two methods, using two methods. Okay, so this is dot product. So let's talk about, and remember I said dot product gives rise to a scalar, right? Dot product gives rise to another scalar. That's why work done is scalar. Work done is what? Scalar. All right. So for cross product, first let me show you the formula, then I'll show you how the formula was gotten. A cross B, vector A cross vector B is equal to the magnitude of A times the magnitude of vector B sine theta. This is pretty much like the cross product, like the dot product. So now, how did they derive this formula? Now, the phenomenon that we use to explain it is torque, the phenomenon of torque. Now, you know, torque is the action, is when two forces, two concurrent forces are acting on a body. They are equal and opposite, so they will cause what? Rotation of the body. This is different from your weight and normal reaction. Your weight and normal reaction are not, they are concurrent, but they are co-initial and they are collinear. Your weight and normal reaction. Your weight is acting between your leg and the ground. Your normal reaction is acting between the ground and your body back. So normal reaction and weight. They are collinear, so they cancel out. So that's why you are not rotating. You are able to stand. But for this guy, when two forces are acting on opposite sides, number one, they are anti-parallel. They're anti-parallel and they're acting on different sides, the opposite ends of a material. I've showed you this in electric. For example, if we have a dipole in an electric field, a dipole in an electric field causes the dipole to rotate. So that's torque, a turning effect of forces. Torque is the what? Turning effect. If you want me to release a video on that, just mention in the comment section. The turning effect of forces. Okay, now here's my point. Now, torque was used to explain the phenomenon of cross product. You know that the formula is also force times the arm, right? Fr, right? That's torque also. But why is this different from work done? Now, here is the case. Consider this situation where you have a door like this now. So you have a door and you want to open. How do you open this your door? So let's say this door was like this initially. It was closed. And you are at the door. You want to open the door. So you stretch your hand to the knob and then you twist it and push. Now your force is going to go in this direction. Now what will happen is that the hinge of this door here will cause this thing to rotate. So this thing will rotate. If my door now, let's say my door is on this plane now. If I push it, let's say we push it down. Let's say inside is down. In this case, my door is now flat. Inside is down. I push it. The edge of the door, this door now is pushing. The edge of the door will rotate, right? The edge of the door will move in this direction. Does that make sense? The edge of the door will rotate like this in this direction. Okay. But your force went in a straightforward manner. Your force pushed it in this direction. Your hand pushed in that direction, straight down. Does that make sense? Okay. Now, we want to analyze the component of the force that you applied that caused this thing to actually move in that direction. Now, when I use this direction, this for explanation of door, opening the door for students, they didn't understand that much. So I like to use the one for spanner. If I open spanner, if I want to rotate a wrench if I want to open, loosen or tighten a bolt, I'll rotate a wrench, right? So let's say this is my spanner here. This is my spanner. I like to, let's say we brought it from this position here, as it is like this. We brought it was here initially, and want to rotate, want to open this guy here. Let's open this guy here. So we are, okay, we're trying to open it. So this guy will now turn, we brought it down in this direction. Direction matters now because we are under torque. All right, so take note, take note. You will understand, just stick with me, stick with me. So our guy has come like this now. Our wrench has rotated to this direction. So this is the new location, this is the new position. So this that you have here is the initial position, or was the initial position. So I'm putting it in broken line to show you that it's the original position. So look at it, we want to rotate this in, so we are bringing it from here down, right? So what's the direction of our force? Our force came from here to this place. So we apply force in this direction. So if we draw our Cartesian coordinate on this thing, so I'm going to clean that of the door now. If we draw our coordinate on this thing, what you will see is there are two components of the force, like we had before. I'm separating this guy. So there are two components of the force. There is one on x component here, there is fx component here, and there is fy component. So this fx component, we can repeat it here so that we'll close this side here. So this is fx component, or repeat this fy here. Do you understand? Any way you want to do it. Now, which component of this force caused this guy to move, caused the rotation of this guy? Which component of the forces? Now, where did this head, just look at it, where did this head move from? It moved from up, down, isn't it? It moved from up, down. So if it moved from up, down, then the component of the force, and our angle is usually viewed to the horizontal, right? Let's take our angle to the horizontal. Now, which component of this force caused rotation? Okay, so which component caused it is this component here, the up to down, that is down. So that's vertical axis caused rotation. So this is Fy. So what we have is, there's an angle here, this angle here will be equal to this angle here. Do you agree with me? Z. So we have this, something that looks like this, right? So this is our main force, the force we apply. This one is the x component of the force, this is the y component of the force. These are our theta that will view to the horizontal like we did in the other case. Now, the component that will cause this guy to rotate, this thing to rotate, is the component that is bringing, which direction is this guy moving? He's moving down. He's not moving up. We are not bringing this thing like this. We are bringing it down, right? Okay, so since we are bringing it down, it means it's the Fy component that contributed to the motion. Do you understand now? So. But this guy, the arm actually moved. The arm is actually in this direction. Look at it. The arm is in X component. I hope you understand. The arm, R is the arm. You know, it is force times the arm. In our door thing, the distance away from that hinge times the force, that's torque, right? In this case, is the arm, the length of this thing, times the force applied. That's the torque for the rotation of this wrench. Now, so Fy is the one that caused motion, because we said it's this guy, right? So if we analyze this thing, Fy is what we know. Fy is opposite. F is what we know, rather, F is what is given. This is our right angle. Fy is given. Fy is the one that is causing motion. This is opposite, right? So, and this is hypotenuse here, right? So which function combines them? Sine. So sine theta is opposite over hypotenuse. What's our opposite in this case? Fy. So sine theta will become f sub y over hypotenuse is f. So that our force Fy now becomes, by the time we cross multiply, Fy becomes this times this f sine theta. Does that make sense? So the component of the force that caused rotation is Fy, that caused rotation on this guy. So if we now want to calculate the torque, the amount of rotation caused, the amount of rotation that is caused, that's the torque, that's going to be the force. Which component? The component that caused rotation times the arm. Okay, that becomes F sine theta dot displacement. Does that make sense now? So in perspective, it means that we are multiplying. So the cross product is the product of the first force, the product of the first vector, the product of the first vector, first vector, and the component of the second vector that caused motion, that resulted in what? Motion. The component, I'm sorry, the component of the second vector that caused motion, the component of the first vector that is, now, what's the relationship between this guy, Fy and R? They are perpendicular, right? So it's the component of the force that is perpendicular to the first. Because it's that one that is perpendicular that will cause motion, not the one that is in direction of it. The one in direction of this does not cause motion, does not cause this body to rotate. It is the one that is perpendicular to it that is actually causing this body to rotate. Now let's talk about direction. This is where I want you to understand so that you will not cram. Now, think of this as we are trying to loosen this bolt. As we are rotating the spanner like this, and rotating the spanner like this, what will be happening to this guy, this direction, if we are turning something like this? Look at this thing now. Look at my marker. Look at this marker. If I turn it in this direction, my force is coming down like this. If I turn it in this direction, what is happening to this cover? Look at it. I'm going like this, right? So let me turn it back. Since I'm going like this, watch out. What is happening to the cover? You see that it is going up, right? So if I turn it like this, it will be coming out of the board. Good. So this is the way we do it actually. We use the right hand rule to get the direction of movement of this guy. We'll fix this is the right hand rule. We use our fingers like this. My hand is very black because of the black marker. So, but I'm not black, Jerson. So we have two forces here. We'll put these two fingers, these two fingers, in the components of the two forces. Then the third component, this one will be the direction of the force. Is that clear? I'll teach you two methods of doing that. So if I place my two forces like this, here's my first force and my second force. Since these are the direction, you see, where is this hand moving? It's moving out of the board. Look at it. It's moving out of the board if I composition it well. It's moving out of the board. Now another way to view it is to do it like this. That is because I'm moving in that direction. If I'm moving in that direction, exactly, you see that it's into the board that way. So now what? The other way to know direction is this. Use the Maxwell's corkscrew rule. So if I'm rotating this cork like this, the cover of something like this, if I'm rotating it like this, so it means I'm going like this, right? So as I'm going like this, what direction am I going? My thumb, the direction that my thumb is pointing is the direction of the third vector. See, I'm going like this. If I'm going like this now, you know, if you are tightening, if you are going like this, it means you are losing something, right? You are losing something. So you are loosening, not losing, loosening something. So it means you are going like this. So where's your thumb pointing? Out of the board. So it means it will go like this. Make sure you get that. In fact, this master corkscrew works well. If I'm now turning something like this, let's say if I'm tightening something, where would this thing be going? To be going down, right? So see, where is your thumb pointing? If I'm tightening it like this, my thumb is pointing down. So the direction of my thumb is the direction of the third force, which is the force that's being produced here. So this guy will be going down, exactly because I'm turning like this. Do you understand now? If I'm turning like this, counterclockwise, opening, coming out of the board, closing into the board. Is it clear? All right. That direction I just showed you now is very, very essential in physical representation. So I'm going to clean all of this now. So you can see f dot r sine theta. First vector times second vector sine theta. So now let's go to physical representation. This is where you have to really listen. You have to really, really listen. Now watch. I want to multiply vector A, take the cross product of vector A and vector B. And I have AXI plus AYJ plus AZK times BXI plus BYJ plus BZK. All right. So the same way, if we multiply this guy by this guy, it's going to give us AX, BX, I cross I, sine theta. We'll talk about the angle between them soon. Plus AX times BY now. AX, BY, I cross J, cosine theta. Plus AX, BZ, I cross K, sine theta, plus AX, we are done with AX. Now let's go to AY. AY, BX, IJ cross I, sine theta. Plus AY, BY, J cross J, sine theta. Plus AY, BZ, J cross K, sine theta. Plus A, we're done with AY, right? Now let's go to AZ. AZ, BX, K is now crossing I, sine theta. Then AZ, B plus AZ, BY, K cross J, sine theta. Plus AZ, BZ, K cross K, sine theta. That's all, right? That's all. All right. So listen carefully. Some will still turn to 0 here. Well, let's know which ones now. Watch closely with me. We have BX. I'll tell you the rule later. The rule that was, you probably have seen this before. You would have seen this before. I, J, K. And they tell you I cross I is equal to K. I want to show you how this was invented. Is that clear? I want to show you how it was invented. Now watch. AX times BX is I cross I sine. What's the angle between I and I? 0. And sine 0 is what? 0. So this will become what? 0. So we have vector A cross vector B is equal to 0 plus. So that's why if you see I cross I in your formula, he'll tell you that I cross I, let me bring it in. I cross I is 0. Is it clear? Because if you put the component of the first force and the component of the second force that is in the direction of the first force together, you cross them together, you get 0. Is that clear? Good. From this formula. Now look at this one now. We now cross I and J. Let's cross I and J. Let's see. I, where is I direction? I is in this direction, x-axis, right? J is in this direction. Let's cross it. How do we cross it? Cross I and J. I is here, J is here. So we cross like this. If we cross like this, our thumb is pointing where? Outside. What is outside? K direction. Do you feel me now? We cross this, we cross it, then it gives us K direction. Does that make sense? From I to J, we are crossing I and J now. Cross it, it gives us this direction. So it gives us K. So, and the angle between there is what? 90. And sine 90 is what? 1. So it becomes AX BY K. Does this make sense now? Good. Can put them together like this. Then plus this guy now. Let's do this. I cross K. Let's see. I cross K. Now, how do we cross I and K? This is K is out of the board. See. K is out of the board. I is here. So let's cross it. If you want to cross I and K, see, cross I. This I and K. So it means we are doing like this. No, we are doing like, how do you cross this? Yes, like this. See, you are crossing it like this. This is how you cross it. Or how do you cross? Like this rather. So you are rolling in direction. You see, as you are crossing it, it's like this. Do you understand? See, like this. This is how you cross it. This is how you cross this. Not like this. You are not crossing them like this. You are not crossing them like this. See, you are crossing them like this. See, like this. If you do like this, you are not crossing this two. See, what you cross like this is, see the direction. I cross J. That was what we did the other time. That was how it was out. Now I want to cross K and I. So this is how we do it. You bring this K and I from, you are going from I to K. So you are doing like this. So you are crossing. Which direction is this? Negative J. So that becomes AX BZ. So times minus J. So this minus can come forward here. So we say minus AX BZ J. Does that make sense? So if you cross I and K, first we have discovered if you cross IJ, IJ will give you, I cross J will give you what? K. When now we cross I and K, what did he give us? Give us negative J. Alright. I'll teach you the sequence, the formula, the fastest way to get that. But I want to show you how it was invented. You have seen it before. I've seen it before. I have a message. Yes. All right. So I'm going to rush this quickly because my phone space is now is diminishing. So we said, so this guy AXBZ gave us negative G. Then plus, how about J cross I? How do we cross J and I? So this is J, this is I. So if we cross J and I, our hand must move in the direction of J and I. J and I, how do you cross it? That's like doing like this. Yes. So your hand must be open like this. J like you are crossing like this. So we are crossing J. No, positive J. We are crossing positive J, right? And I. We are crossing positive J and I. So let's cross positive J and I. That becomes like this, right? We are going from this direction, so we are crossing. So which direction is this? When you cross like this direction is what? Into the board. That's negative K. Into the board and out of the board is K. So this becomes AYBX into bracket K. We know this will now be negative because it's negative K. Then plus J cross J. If it's the same distance, 0, sine 0 is what? 0. So this one is also 0 plus this last one will be 0. KK, right? We already got that. Now J cross K. If J crosses K, you can just be trying that. I will not be showing you all of that again, okay? So if J cross K, this is the last one I will do, okay? J wants to cross K. K is in this direction. Into and out of the board, right? Into the board is K. This is J, positive. So we want to cross it now. What will happen? See, cross. Do you see that now? We'll cross J and K. What direction is this? I, right? Yes, that's I. So that becomes AYBZ I. Does that make sense now? Then minus A, K cos I. Now, if I cos K to give you negative J, then K will cross I to give you J. Well, you can prove that. You can check to prove that, okay? That's plus. Okay, let's quickly check that. K is crossing I. K is crossing I. So, K is crossing I. This K out, I. Cross it. Do you see that? That is upward, that's J. Alright, positive J. Then, K is crossing J. Have J crossed K here? J has crossed K, gave us positive I. So if K crossed J, the opposite, negative I. I hope you understand what I just did. Negative I. I'll show you the trick. Negative, I'll put the negative outside it, then I. Then plus 0, this will be 0. Then I'll show you the matrix method of actually solving this. So our final answer, A cross J cross B, becomes AXBY minus AXBZ, K, minus AXBZJ minus AYBXK plus AYBZI plus AZBXJ plus AZBYJ. So we have to collect like terms, the ones that are like JJs, bring them together. So our dot cross product, the final equation of our cross product, I'll give you the tricks and so on, just watch. So I can go directly from here to here. You'll see how I'll do that. K and K, which ones are K's? Let's do I's first. This one is I. They have to be 2, right? They have to be 2. 1, 2, 3, 4, 5, 6. So K and K, J and JI and I. So that will be, so this is I, sorry. So, and this I is negative, this I is positive. So let's bring this first. So it becomes AYBZ I minus AZBY all I. Make sense? Then plus J is next now. J is next. Which do you have a positive J? Yes. AZBXJ. So AZBX minus which other J? AXBZ. J, then plus a positive K, AXBY minus this, the next one will be BXAY, you see. K guys, right? BXAY, so AYBX, K. So this is the final answer for A cross B in physical representation. So this is what you have. Is it clear now? So now here's the trick. So just use I, J, K. When you cross I and J, you get this. I cross J, you get K, the next one. J cross K, I, J, K again. Let's put I, J, K in front again. So I, J, K, I, J, K. I cross J, K. J cross K, I. Is that clear? Then K cross I. K cross I will give us the next one in front, which is what? J. Is that clear? Once you reverse this, J cross I will give you minus K. K cross J will give you minus I. And I cross K will give you minus J. So if you use this to verify all that we have done, you see that we are correct. And I cross I 0. I cross I is the same as J cross J, which is the same as K cross K, which is equal to 0. Is it clear? Now let me show you the last thing, which is the matrix method of determining this matrix method. So I'll write the same question Or you see it to be faster now, but I just wanted you to see physically. That's why I made this video this long. So please, I pray God will bless you as you watch this video till the end, because I know that it is long and time consuming, but you know, God will bless you and you'll pass your exam, you know. All right, let's go. So if you want to cross this, we can use matrices to do that. So what we'll do is, all these guys are our I's. All these guys are our J's. These guys are our K's. Make sense? So we now have AX and BX are under this place. AY and BY are under this side, and AZ and BZ are here. So by the time we use vector, determinant, to use determinants, our A cross J, A cross B will cover this place for I. For I, we'll cover this place and we'll have this, cover this place and this place. Do you understand? To get the values of I, we'll cover this place and this place. Exactly. We'll now multiply this times this, AY times BZ. For I, we have AY BZ minus the second diagonal. Mean that is, determinant is always mean diagonal minus minor diagonal. So we have here, major diagonal is AY BZ, minor diagonal is AZ BY. So minus AZ BY. For I, let's check. AY BZ minus AZ BY. Do you see that? You can put your I here. So plus for J now, we'll cover here, cover here. Exactly. We'll cover here and cover here. So it will be AX BZ. AX BZ minus AZ BX. I hope you are seeing it. I hope I'm not covering what yours. What is it? AZ BX. Let's confirm that. AX BZ minus AZ BX. Okay, there is a flip here. I think it's just the sign. It's because of the sign, okay? It's because of the sign. Maybe we made a mistake here. It's supposed to be a minus here or something. That's the only problem. Oh, yeah, I remember. Sorry. It's my mistake here. You are supposed to put plus, minus, plus here. That's how you find determinant. I'm sorry. So here is going to be minus. So if you multiply this out, it becomes AXBZJ minus AXBCJ minus AXBCJ. You see that? Minus and minus plus AXBXJ, AZBXJ plus. Exactly. By the time this opens the bracket, it gives you the same thing. Is it clear? Then plus, close this guy, AXBY, AXBY minus AYBX. Positive. Okay, K. All right, so that is our final answer. So you now understand, I assume now that you understand everything about vectors. Now to use this to solve question, very simple. Take the magnitude like I taught you, times the magnitude, sine the angle you are given. Is that okay? Which means that if you are told to find the angle, you just take, since A cross B is A magnitude of A times magnitude of B, sine theta, then theta will be equal to the sine inverse of A cross B over magnitude of A times magnitude of B. Is that clear? So this will be it for this video. Do what, subscribe to the channel and click the bell notification. God bless you as you subscribe. Amen.